Okay, now we're actually going to start looking at this worksheet. So, we're going to start with our acetic acid equilibrium. Now, I don't love the way they wrote it up here. I personally would rather write it like a classic weak acid equilibrium, and instead of showing hydroxides in it, just realize that the hydroxides remove the hydrogen ions. So it starts out looking like this. It's our classic acetic acid, weak acid equilibrium. Now it's nice that they put everything in 1 liter so that moles are the same as molarities. So 0.1 moles of sodium hydroxide are added to 1 liter of 0.5 molarity acetic acid. It will react to form a solution which is 0.1 molar acetate ion and 0.4 molar acetic acid. They really walked you through this. They didn't have to tell you this part or this part. You should have been able to figure it out. Let's see how. So your initial amounts, they told you start with a 0.5 molar acetic acid solution, and then you're going to add 1 mole of sodium hydroxide, and it's 1 liter. So 0.1 mole of sodium hydroxide. What the sodium hydroxide does is it just removes the H pluses. And the H pluses and the OH minuses become liquid water. So every bit of hydroxide that's added shifts this equilibrium to the right and takes those H pluses. So when I shift this to the right, I'm going to write here for this, the acetate ion. I'm going to write here for the acetic acid. But this column here with the H pluses is actually going to be a bit of a mystery because it shifts right, it makes more, and then they're immediately taken. So 0.1 mole. Okay, strong base. The strong base that's added drives the reaction to the right. So this is like plus X minus X. Except we know what X is. We know how much it's being driven to the right. It's being driven to the right 0.1 moles. So of course, the final amounts, there we go, are 0.1 molarity of the acetate ion and 0.4 molarity of the acetic acid. Now, what's going on right here? As it shifts to the right, it makes the same amount of H plus as the acetate ion, but they're also being taken away by the hydroxides. But it is an equilibrium of a weak acid with a very small Ka, so there will be small numbers here. We don't care what they are. That's the nice thing about the Henderson-Hasselbalch equation. The molarity of HA is in the Henderson-Hasselbalch equation. The molarity of A minus is in there, but we don't actually have to know the molarity of the H plus, because that part of the equilibrium expression is replaced by pH. Negative log of H plus is replaced by the pH of it. Okay, so what is the pH of the solution? And they told us the pKa is 4.76. They could have told you the Ka, and you would have taken the negative log of it to find the pKa. Either way, we're really good with the Henderson-Hasselbalch equation. Okay. So here's what they gave us. The pKa is 4.76. This is my Henderson-Hasselbalch. I can see where that's going to go. I can see where my molarity of A minus goes and my molarity of HA. So we're going to use this equilibrium a bunch of times. Just remember, however much strong base is added, that's how much it's driven to the right. So clearly, this is just my 0.1 over 0.4. That guy over that guy. If there's a tiny change, if there's a tiny shift in the equilibrium that changes these molarities, it's going to be very small compared to these molarities. The Ka has to be pretty darn small. So if this is a tiny bit less or this is a tiny bit more because of a tiny shift to the left, because this can't actually be 0, we're not going to worry about it. It's going to be orders of magnitude smaller. Now it's just a plug and chug. You just solve it and you find your pH. You find your pH to be 4.16. Okay. So that is our answer to number 1. The pH is 4.16. For number 2, we have this big old chart. we just did this. 0.1 moles of NaOH added, 4.16. The answer here was 4.16. Okay. For this one, and this one, it's just more NaOH, so we just shift it more to the right. Imagine how it's going to be different. Okay. If it's 0.2 moles of NaOH, I get 0.2 here, minus 0.2 here. I'll do that. Plus 0.2, minus 0.2. However much NaOH is added, that's how much it shifts. So of course my final amounts here are 0.2 and 0.3. And these two numbers go into Henderson-Hasselbalch. When it is 0.3, this is plus 0.3, that's minus 0.3. That would make that 0.2, and so on. And that works for these three guys. Okay? So notice, however much it shifts, that's how much more of the acetate ion I get. So, see how this number and this number are the same? That makes sense, because you shifted it to the right by that much. So this guy's 0.2, 0.3, 0.4, and I'm going to leave this blank for now. This is the original minus the shift. So 0.5 minus 0.2 is 0.3. 0.5 minus 0.3 is 0.2. 0.5 minus 0.4 is 0.1. And then you, hopefully, let's see, you're just going to plug into this fraction over and over and over again. For example, for this column here with the 0.2 shift, let's see, that's the acetate, that's the acetic acid. So this fraction would be 0.200 over 0.300. That would go in right there. And I take the log of it, add it to 4.76, and I have my pH. For the next one, acetate over acid, 0.300 over 0.200. And for the second to last one, 0.4 over 0.1. Okay, I'm hoping that you did that. And if you did not do that, pause this right now, try the math out, and see what pHs you get for those three. So hit pause. And here are your actual answers that you can check. I got 4.58, 4.94, and 5.36. Now, I'm not sure what they expected you to do here, because what could you possibly do here? 0.5 over 0 and take the log of something divided by 0? So I'm hoping that this was a little bit confusing until you got to the back. So we're going to save this for the back. Okay, this we know though. To react completely with the original acetic acid, 0.5 moles of NaOH must be added. What is the pH of the solution when exactly half this amount is added? We should know what's happening here. We are at the half equivalence point. So look back at your notes. You take Henderson-Hasselbalch, and we should know that at the half equivalence point, the molarity of acid equals the molarity of conjugate base. This fraction equals 1. Log of 1 is 0. And your pH equals your pKa. So of course, the pH would be 4.76. That's only true at the half equivalence point. The pH equals the pKa. Okay, so I would just describe that here. How do you obtain the value for pKa for an acid? Okay, now let's go to the back and let's look at this situation here where we've gotten ourselves to the equivalence point.